So good evening. So today we will see the problem solving session 11 on the topic adsorption and ion exchange. So here is a brief recap. So first two topics we saw in the last week. Now in these sessions we are going to solve the problems fluidized bed and tether bed, steady state moving bed adsorber, then a steady state fixed bed adsorber and ion exchange. So based on these topics, we are going to solve the problems. So starting from the MCQ one, what is the major use of carbon molecular sieves? CMS, short forms, right? So check the options. The separation of the lowest hydrocarbons. So generally for the separation of the lower hydrocarbons, use the zeolite and ZMS. The full form of ZMS is a zeolite molecular sieve. And option B, the adsorption of organic from the drinking waters. So here the adsorbent is as a activated carbon. And separation of air to the to produce N2. So here the CMC is used, carbon molecular use adsorbent. CMS. And option D is removal of the organic from the gas streams. The polymer adsorbent. Right. So options. Question number 2, if the adsorption rate of solute is infinitely fast and irreversible, the thickness of empty Z means mass transfer zone would be. So if the adsorption rate of solute is infinitely fast and irreversible, so solute will be the adsorb immediately upon contact with the adsorbents, leaving no time or region for a gradual mass transfer. Therefore, the MTZ mass transfer zone would especially shrink to zero thickness because solute concentration would drop to zero. So option C. Question number 3. The length of unused bed is more if the mass transfer zone. Uh, Length of unused bed increase when the MTG is widest because saturation progress more gradually across the bed and leaving the sorry. Okay, the length of the unused bed is more than mass transfer zone is wide, and vice versa. The length of unused bed is less. The mass transfer zone is narrow. So option A is correct one. Move to the question number 4. The breakthrough point is decreased by. So, so the breakthrough point is decreased by the increase the particles of the adsorption, increase the concentration of solute in the feed, since you say increase the flow rate, and D decrease the bed depth. So all these factors are important to decrease the breakthrough points. So option E is correct one. Moving to the question number 5, adsorption capacity of regenerated bed compared to the fresh bed is generally slightly less. Which correct. Question number 6, how is a breakthrough concentration defined for the adsorption in a packed bed? So the breakthrough, it is the minimum detectable or a maximum allowable concentration in the effluent from the bed. Right. This is a breakthrough concentration in the adsorption bed. Question number 7. Ion exchange region is a organic polymer with a porous structures. Option C is correct one. Question number 8. Ion free water coming out from the exchanger is known as demineralized water, because removal of the ion from the waters. That's called the demineralized waters. Now question number 9. So here we have to tell this is the set is this statement true or false. In a PSA systems, pressure swing adsorption system, adsorption of solute occur at a higher pressures. So in a PSA system, the adsorption solute occur at a higher pressure. So this is a true statement. Question number 10. The adsorption occur at a lower temperature in a temperature swing adsorption systems. So in a TSA system, so adsorption occur at a lower temperature. So this is also true statements. So moving to the numericals. The here is a statement: the velocity of MTG, mass transfer zones, for adsorption of a solute in a packed bed is 5 centimeter per minute. This is a velocity. The length of bed is 120 centimeter. The equilibrium time is 26 minute. Right, length given. Then we have to calculate the what is the thickness of the MTZ, and second part is the what percentage of bed remains unused at a breakthrough. Right. So to calculate the mass transfer thickness of the mass transfer zone, MTZ thickness, right? So here formula MTZ velocity into equilibrium time. Right. So MTZ is a velocity given 5 centimeters, 5 centimeter per minute, and equilibrium time is a 26 minute. Right. It's a 130 centimeter. Right. So this is the thickness of the MTZ. Now this is the first part. Now second part. The percentage of bed remains unused. So to calculate this percentage, here is a formula: unused bed percentage equal to MTZ thickness divided by bed length into 100. Right. So the thickness of MTZ we calculated 130 and bed length is a 120. Right. So 130 divided by 120 into 100. Right. 108.33%. Since MTZ thickness is 130 centimeter is greater than the bed length, that's a 120 centimeter, right? So the result indicates that the empty shed exceed the bed length. This implies that the entire bed is used before the breakthrough occur. So therefore, 0% of the bed remain unused at breakthrough. Breakthrough because MTG MTZ has already covered the entire bed. So in this questions, we calculated the thickness of the MTZ, then percentage. So here the uh, MTZ thickness is 130, so it is greater than the 120. So 0% of bed remains unused at a breakthrough. Moving to the question number 12, an experimental packed adsorption column of 0.5 meter bed depth is used for the breakthrough study of a dilute wind streams having 0.02 mole fractions of volatile organics. The breakthrough curve is symmetric and the effluent concentration is 0.01 mole fraction at 60 minutes. It is also found that it takes the 15 minutes for the effluent concentration to increase from Y 0.004 to 0.0196, that is the 2% to 98% of the effluent concentration. What is the length of the MTJ in the centimeter and velocity of empty mass transfer zones? Then what bed height would you recommended if 90% of utilization of the bed is to be achieved under the same operating conditions? What is the breakthrough time for this bed? So in this question, we have to calculate the length of MTZ, then velocity of MTZ. In second part, so what would be the bed height would be recommended if 90% of utilization of the bed, right? Then what is the breakthrough time for this bed, right? So here mentioned that the time to reach C by C naught. Here C by C naught. Okay. The final effluent. Okay. So 0.1 divided by 0.02, that's a 0.5, right? At the bed exists, right? The time required 60 minutes, that's a TM. A bed length is a 0.5 meters. So convert 0.5 meter, convert into the centimeters. 50 centimeter, right? Now first calculate the velocity of empty jet. U is equal to L by Tm. Right. So here is A is a 50 centimeters, Tm is a 60 minute. Right. So 0.33 centimeter per minute. Now it takes a 15 minute for the mass transfer wave front to move. It takes 15 minutes for mass transfer wave front to move through its own length. So taken as a C by C naught equal to 0.02 to 0.9. Right. Now length of empty jet it 33 velocity into times so 12.5 centimeters. Right. Now we have to calculate the second part. What bed height would you recommended if 90% utilization of the bed is to be achieved under the same operating condition? So what is the breakthrough time for this bed? Right. So now length of unused bed L UV. So length of empty jet 12.5 divided by 2. Right. It's a 6.25 centimeter. The unused bed, assuming the symmetric wavefront. Symmetric wavefront. Okay. For 90% bed utilization, L minus LAUV, length of unused bed divided by F equal to 0.9. Here is a 90%, right? So 1 minus LUV 0.9, right? So LUV here is just 6.25. So L is a 62.5 centimeter. So long bed to be used, right? Right. Now, what is the breakthrough time for this bed, right? So to calculate the breakthrough, that is denoted by TB equal to LS VS, right? So 62.5 minus length of unused bed 6.25 divided by velocity 0.833, right? Sixty-two point five minus 6.25, 67 minutes. 5 minute. So 62.5 centimeters height up bed recommended for the 90% utilization, and the breakthrough time is a 67.52 minute. Moving to the question number 13, water containing 120 ppm Ca plus 2 plus Ca2 plus is to be treated with an 8% DVB cross-link reagent in a Na plus form to remove the 90% of the calcine ions. The reagent has an exchange capacity to equivalent per liter. Calculate the amount of reagent required to treat 10 meter cube of the water. Right. So here is a equation given. So selectivity coefficient KCa plus divided by Na plus equal to 2.6. So for a region phase, the total concentration of X inside CE, right? E to equivalent per liter, right? Now total concentration of ion in solution Ca plus plus and Na after exchange expressed as a Ca plus plus ions equal to, here is a 120 ppms, right? So 1000 ppm is equal to 1000 ppm equal to 1 gram per liter, right? So it convert into the gram per liter. So it's a 0.12 gram per liter, right? Now we have to convert into the gram equivalent. So the gram equivalent is a weight Where I can write down. Equal to weight divided by equivalent weight. Okay. And equivalent weight is a molar mass divided by n, number of vacancy, number of charge. Right. So here 0.12, here is n, so 2 divided by 40. That is a 0.0006 equivalent liter. It is a C. Right. Now 90% of the C ions remove at the end of the equilibrium contact. Right. Ions removed at the end of equilibrium contact. Right. Now Ca plus ions remaining in the water equal to 0.05 into 0.06. Right. Equal to 0.0003 equivalent per liter. Right. Now equivalent fraction of Ca plus water equilibrium xt equal to 0.003 divided by 0.006 to 0.05. Right. Now if Yd is a equivalent fraction Ca plus in the region phase in the now we have to use the equation Yd 1 minus y d square equal to k dB Ca x d 1 minus x d square, right? So here you have to calculate the yd. So k if given, select coefficients, say 2.6, say e is equal to say e 0.06, right? XD here 0.05, right? So after calculate the yd, we get 0.8657. Now total amount of calcium, ions in a solution equal to 0.12 gram liters into 10 meter cube. So it's a 10 to the power 4 liters. So 1200 gram. That is a 60 gram equivalent Ca plus plus, right? So iron removed, 60 gram equivalent Ca iron removed into 60 into 0.95, that's a 57 gram equivalent. If m kg region huge, quantity of exchange site is twice m into equivalent. So fraction 0.8657 of exchange sites now occupied by Ca plus plus ions. So twice m into 0.8657 into 57. So quantity of regions is a 30 kg. So 33 kg of regions required to treat a 10 meter cube of the waters. So I covered all the questions based on this, based on the topics of this week. So we will meet on next Friday on next chapters. The crystallization. Thank you.